So we've been talking about when functions are well behaved, it's easy to find the limit because it comes down to a simple plugin for all those previous examples. Now we got to start looking at what if a function is not well behaved. And again, I understand we haven't really said what well behaved is, but let's take a look at this. Functions that agree at all but one point. So let a be a real number and let f of x equal g of x for all x not equal to a in an open interval containing a. If the limit as x approaches a of g of x exists, then the limit as x approaches a of f of x exists. And on top of that, the limit as x approaches a of f of x equals the limit as x approaches a of g of x. So what does this really mean? Well, what we're saying is that if you think of this as a function with a problem. So f of x has a problem at a. It's not well behaved at a. But g of x is well behaved at a. And f and g are the same function, exact same function, except at a. So what we're going to do is, in order to figure out the limit of f at a, we're going to use the limit of g at a. So we're going to just use g to get us the information about f. Okay, and so as long as they differ by only 1 point, that may sound like a strange thing, but there are a lot of functions that differ by just 1 point. So if we have this f of x with a problem at a, and we can find a nice g of x that's good at a, we can do the limit of f. Okay, maybe, a nice example of this graphically would help. All right, so the idea is, we saw this before actually when we were starting the graphical introduction to limits. Let's say the graph on the left here is f of x, okay? So f of x is this line with a hole at the point 1, 2. So this was like the x squared minus 1 over x minus 1. So it's the line x plus 1, except it has a hole at 1, 2. G of x is the same function without the hole. So now graphically, we were still able to do the limit of f of x, but where this is really going to come into play is analytically, when this is really behind the scenes. We're not seeing this, but we're going to understand that that's really what's happening. So the idea here is that I can do the limit as x approaches 1 of g of x. Even if I were just to do this analytically, I would be able to figure out that that limit is 2. And then I would be able to go over here, and because f of x is the same function, except it only differs at the point of interest, the limit of f of x is going to be 2 as well. So again, this doesn't seem like a big deal right now because we're just looking graphically, but this is really what we're going to be doing as we move forward and talk about how do we actually calculate these analytically, so just looking at the function and not the graph. So here's how this would work. Okay, so basically the idea is that we can take a bunch of different cases, and whenever we see it developing into that type of case, we know what's going to happen and what we should do. So the first case is dividing out in what I'm calling an existing common factor. You'll see what I mean. So if I wanted to do the limit as x approaches 2 of x squared minus x minus 2 over x minus 2, okay, a good first approach, again, is to just plug in the point of interest. So if we just go ahead and plug 2 in the numerator, we'd get 2 squared 4 minus 2 minus 2, we'd get 0. In the denominator, 2 minus 2 is 0. Okay, so we get 0 over 0. This is what's called indeterminate. All right, so this is very important. An indeterminate limit value here is telling us that literally what it says, we don't know what it's determined to be. It might be might not exist. It might be 3. It might be infinity. It might be -1/2. We just don't know. But in this case, knowing it's 0 over 0 gives us a goal of what we should try and do. Basically, it's saying there's something causing 0 in the numerator and the denominator. So what we should do is look to factor. All right, so if we factor x squared minus x minus 2, we would get x minus 2x plus 1 over x minus 2. Okay, so now we see, and it's no surprise that there was an x minus 2 factor in the numerator because it was 0 when x was equal to 2. All right, for a polynomial, that's a rule. So what we're going to do now is, normally you would not just cancel out factors in a function, but we have a special case here. We're only looking at the limit, and the limit doesn't care what's happening at the point. So we can go ahead and cross out the x minus 2 factors because the limit doesn't care. And so what we'd have is, we'd have the limit as x approaches 2 of x plus 1, which is now a simple plug-in. Plug in 2, and we get 2 plus 1, or 3. So in that way, we just found this limit by looking at a simpler, nicer function. So essentially, I mean, that's the problem there, but I want to point out that basically the idea is, from what we were talking about before, the f of x is this function, x squared minus x minus 2 over x minus 2, and g of x is x plus 1. These two functions are exactly the same except at x equals 2. So if we want to do the limit as x approaches 2 of this function, which we can't directly do, we instead use this function, which can be used at x equals 2, and we'll get exactly the same answer. And this one is the easier one to evaluate. Now basically I called that an existing common factor because it was easy to factor that out. Okay, it wasn't sitting there originally, but it was easy to get that x minus 2 out of there to be canceled. A little bit more complicated of a case is what I call creating and dividing out a common factor. We're not really creating it, we're just bringing it out, but I thought it was a nice way to look at it. So again, if we're trying to do the limit as x approaches 0 of this function, let's try plugging in. Plug in, and I get the square root of 0 plus 100, so that would be 10 minus 10, so I get 0 on top. And if I plug in 0 on the bottom, I get 0 on the bottom. So again, I'm in this 0 over 0 indeterminate case. That means I have more work to do. Never stop the problem at 0 over 0, because all 0 over 0 means is there's more work to do. So this is not going to be immediately obvious what to do. All right. So the problem is really that I can't do much with this numerator here. So what I'm going to do is I'm going to multiply by something. And if you remember from pre-calculus or an algebra class, what we can multiply is the radical conjugate. So if I do the square root of x squared plus 100 plus 10, but I have to multiply it by the same thing, over itself, so that what I'm multiplying by is really just 1. So what happens here? All right, so when we multiply the top there, remember we have an a minus b and an a plus b, which would give a squared minus b squared. So we'd get the limit as x approaches 0. So we'd get the square of the square root term, which would just be x squared plus 100, minus, so a squared minus b squared, b is 10, so b squared is 100, over, so that's the numerator, we have x squared. Now the penalty we pay is we now have this complicated thing in the denominator, but you're going to see that that is okay. All right, so that's what we have. Now notice what happens in the numerator there. X squared plus 100 minus 100 is just x squared over x squared times the square root of x squared plus 100 plus 10. Okay, and what happens? The x squareds cancel out. That's exactly what we wanted. That's what's causing the 0 over 0. So simplifying, I have 1 over the square root of x squared plus 100 plus 10 in the denominator. Okay, now it's not as bad as it looks because I can plug in now. I plug in and I get 1 over square root of 0 plus 100 is 10 plus 10, I get 1 over 20, and that's my answer. So again, what did we really do? We wanted to look at this complicated function, which has a hole at 0, has a problem at 0. In fact, it's a hole here. So what do? We look at this function instead, which is the exact same function, except it's actually defined at x equals 0. And so we use this one to get the answer to this one, and that's how we end up with our 1/20th.